But also, I wanted to say, if you've got any questions from
Yeah.
previous papers, we could also look at some of those and address those. Okay.
Yeah.
So,
Shall we do it after this question?
yeah, we're just going to
Yeah.
start off with this just to refresh some knowledge on what we learned last time. Good. So the relative atomic mass for sodium is going to 23, is that right?
Yep, 23 and then 35.5 chlorine.
Okay, good start. Good.
To two decimal places, it's 0.85
Okay. Well done.
moles.
Good.
Do you know for the second part, I can't remember, but do you do 100 divided by the grams?
Nearly there. And if ever you lost like that as well, Jay, you can also
Yeah.
use the units. Okay.
Yeah, that's what I was trying to use, yeah.
Good. So
Mm.
here, that means grams is mass. So the formula
Yeah.
must be mass divided by decimal is a measure of volume. So this must be mass divided by volume.
Okay, so it's just 50 divided by 100 then.
Okay, nearly there, but look at the unit here. The unit is decimeter cubed, and you've dissolved it in 100 centimeter cubed.
Okay, so so is it 0.1 decimeters cubed?
0.1, well done.
Yeah, and then 50 divided by 0.1 equals to 500. equals to 50, sorry.
So we can write, say, concentration.
Yeah.
What the concentration in grams per decimeter cubed. Then we need to divide mass divided by the volume, and that volume has to be in decimeter cubed, and that mass has to be in grams. Okay, so if you use that formula.
Yep, I got 50 grams per decimeters cubed.
50 grams, oh, well, this 100 centimeter cubed is what volume in decimeter cubed?
0.1.
Well done. So you'd have a 0.1 at the bottom, and you'd have a mass of 50 grams at the top.
Yeah.
So 50 divided by 0.1, what would that give you?
Oh, sorry, 500. I was right in the first place.
Yeah, good. So 500 grams per decimeter cube. Which makes sense because if in 100 grams, sorry, if in 1,000 cube, 100 centimeter cube, you've got 50 grams, you're going to have 500 in 10 times this volume.
Mm-hmm.
And that's why,
Yeah.
and 10 times that volume would be 1 decimeter cubed. Okay.
Mm-hmm.
All right.
Yeah.
Next one then, part B.
Is it 8.5 grams per decimeters cubed?
Nearly there. But what units are we looking at?
Moles.
Yeah. So your value for B should be 8.54 or 8.5 if you like, moles per decimeter cubed. Yeah,
Yeah.
good.
Isn't that what I said though? 8.5.
Oh, you said grams per decimeter
Oh,
cubed.
sorry.
You meant
I meant
moles.
moles, sorry.
Yeah,
Yeah,
that's
sorry.
fine, Jay. You meant moles
Yeah.
per decimeter cubed. And of course, then your formula would have changed here. You'd have had
Yeah.
moles top divided by the volume in decimeter cubed. Okay, good start. So it's good to just recap on that little formula and remind ourselves of the changes. We've got something in centimeter cubed and how to convert, obviously, between grams decimeter cubed and moles per decimeter cubed. And it's something that you will also have to be happy with to be able to go from, imagine you were given this solution to say, this is the concentration in moles per decimeter cubed. You might be asked to actually give this in terms of grams per decimeter cubed. So then in this case, you'd just be using a formula where you know to say N is equal to mass over molar mass. So you simply multiply the number of moles by your molar or relative formula mass to get the mass, and then you'd convert it into grams per decimeter cubed. So far, so good?
Yeah, yeah.
Good stuff. Okay, so Jay, your turn now to take to the floor. If you have those questions, we can have a look at the ones that yeah.
I'm just going to put the visual on so you can see.
Okay, cool.
So. Should I just do the ones that I didn't know, or?
Yeah, we can focus on the ones that you primarily found a bit tricky or weren't unsure of.
Yeah, but should I get the exam questions up first? It's just.
Yeah, I'm just trying to remember which paper this is. Not too sure which one it is. Was it the one I sent last time?
Yeah, I think it was the. Do you know the one that has the plum pudding modeling where you have to write a description about
Yeah,
how
okay.
it's compared?
Yeah.
That one.
So let me go to that one then. So sent items. Vectors. Concentrations. So it's not the one from last time because that only had concentration calculations.
Yeah.
You want to show me the? Do you want to show me the paper? Of course, I'm also going to look in your folder because your folder should have
It
some.
starts with like that. I think I'm trying to find it as well. I'm not sure. I
Okay,
think
so
it.
in the folder, chemistry, titration recap, mark yield. Yield is not that one. Balancing practice. Stoic. Could it be this one here?
Yeah, I think it is the stoichiometry. Yeah, it is that one.
Yeah.
I've just found it here. Do you want me to share the screen so you can see which one or?
Yeah, please, Jay.
Yeah. All right.
So is that number one? Starting off from number one. Yeah, let's just have a look. Yeah, that is definitely it. Yep, yep, yep. That's it. Nice one, Jay.
So I think it's this one.
Yeah, cool. All right. Fantastic. All
Yeah.
right. So the plum pudding was replaced by the nuclear model. The nuclear model was replaced. Sorry, the nuclear model is with alpha particle. Compare the plum pudding model with the nuclear model of the atom. Okay. So you said in the plum pudding model, the electrons are arranged in no particular way, whereas the nuclear model of the electrons are arranged in shells. Second, the plum pudding model suggests that the mass is spread out in the atom. However, the nuclear model tells us the mass is concentrated in the nucleus. Okay, you've got some points there that will definitely get you some marks, but you would have probably lost some marks as well. I think what you want to stress first here as well is that in the plum pudding, what you have, or the model of the atom, is such that you've got a positive mass, yes, or a positive atom in which you have negative electrons embedded inside it.
So in the plum pudding, there's a positive mass and a negative
Yeah, so
electron.
absolutely. So it's literally like how you've got, if you think about a plum pudding, so the pudding itself is positively charged.
Yeah.
Yes, and the plums represent the electrons, which are negatively charged.
Okay.
So there is an electrostatic force between those electrons and that positively charged bulk.
Yeah. Okay. Yeah.
Okay. And then next thing is when you look at the nuclear model, which was developed, it says compare the plum pudding model with the nuclear model of the atom. In the nuclear model of the atom, however, what is focused on firstly is that the majority of the mass of the atom is concentrated in the nucleus.
Yeah.
And secondly, also that the nucleus is positively charged because of the repulsion. Yes, between the alpha particle and the nucleus, there was that deflection through large angles. So that means that yeah. And then the other point you want to make as well is that an atom is also mostly space. In other words, there's a huge distance between the nucleus and where the electrons actually orbit. And that explains why a lot of the alpha particles were able to pass through.
Yeah. Okay. And also, do you know how it's 4 marks? How many points would you have to make? Like 4?
4 points, okay, 4 points. So if you make so you're comparing them, so you can obviously, well, definitely, so you just got to think of 4 bullet points. What I would do for a question like this, you might want to talk in terms of bullet points. So
Yeah.
if I, oh no,
Wait, so
oh,
when
you
you mean
can't, you
4,
can't,
like 4 comparisons, or
sorry, Jay.
is it like just 4 comparisons, like 4 comparison sentences, or?
Four comparison sentences. So in the nuclear
Yeah.
model, firstly, you want to state the nuclear model has a concentrated mass, or the mass of the atom is concentrated in the nucleus, number one. Yeah. Number two, whereas the mass in the plum pudding model is distributed throughout.
Oh, okay. Yeah.
Okay. Number two, you want to mention also that the nucleus is positively charged. Yeah. Whereas in the plum pudding model, obviously, there is no nucleus, and you can obviously elaborate about what the plum pudding model looks like. There'd be no harm in also drawing an image as well to show the differences.
Okay, would you get extra?
Yeah. There's no harm in doing that as well, and then you can annotate the different parts to it. Okay.
Yeah.
The other point you also want to make is that so we've spoken about the nucleus being positively charged. Most of the mass being concentrated in the nucleus.
And then the space.
Then the spacing as well between the nucleus and where the electrons orbit.
Yeah.
Yeah. And then also in the nuclear model, electrons orbit through specified regions, whereas in the plum pudding model, there is no orbit that the electrons have. So that's 4 points.
Yeah.
Yeah. I will also send you, I think it might help you as well, I will send you the mark scheme to this as well, Jay. So you can also have a look at what the mark scheme says.
Yeah, that'll be helpful, yeah.
Okay. Next one, Jay.
So the one I struggled on was 2A.
Okay. So it says a student investigated the reaction of copper carbonate and copper oxide with dilute hydrochloric acid. In both reactions, one of the products is copper chloride. Describe how a sample of copper chloride crystals could be made from copper carbonate and dilute hydrochloric acid. Okay, so describe how a sample of copper chloride crystals could be made from copper carbonate and dilute hydrochloric acid. Okay, this strictly was a bit of an unfair question, because I think before you could have answered this, you'd have had to know about reactions between copper carbonate. So do you know the reaction between the result that you get when you react copper carbonate with hydrochloric acid?
No, I don't think so, no.
Okay, so this is more to do with acids and their reactions. So we could look at this in more detail when we get there. I mean, I could give you the answer, but there's no point, because we're still going to have to go through it in some more details. How to prepare these crystals. So it's okay that you gave that on a jump. I've got no problem whatsoever.
Okay. And then I think I got B and C. Are we just going through the ones I didn't know, or? Yeah. Okay, and then the next one was 3A. So 3A was this one here.
3A. Now it says, explain in terms of subatomic particles why the mass number of this lithium atom is 7. Okay, so how did you approach this one? So atoms contain protons, neutrons, and electrons. Okay, so a lithium atom is the symbol 7,3. Explain in terms of subatomic particles why the mass of this lithium atom is 7.
So for it to be 7, it means that there's 7 protons and neutrons.
Well, actually, what the number 3 at the bottom,
means the protons.
That's the number of protons. So there are 3 protons and there are 3 neutrons. Sorry, 4 neutrons, I beg your pardon.
Yeah, 4 neutrons, yeah.
Okay. So what else do we know about where is the majority of the mass of an atom concentrated?
In the nucleus.
In the nucleus, well done. So the relative mass of a neutron and a proton is 1, while the relative mass of an electron is nearly 0.
So wait, say that again. So the relative mass of a proton is 1.
As well as a neutron, they're both 1.
Oh, as well, and then the electron is 0.
It's nearly 0, correct.
That's why all the mass is in the concentrated in the nucleus.
Yeah, so when we're adding up the mass of the atom, we don't bother dealing with the electrons, because they have got near zero mass.
Oh, okay.
Okay, and therefore, hence why the mass number will be dictated by the number of neutrons and protons. So you can also start it off as that sentence to say the mass number of an electron is dictated by the number of protons and neutrons, each with a relative mass of 1, whilst the mass of an electron is nearly 0.
Yeah.
Okay? And then the next thing you can say, in this arrangement, we have 3 protons and 4 neutrons.
Yeah, 3 protons.
Yeah,
yeah.
where each one is taken to have a relative mass of 1. Therefore, the mass number of the lithium atom here would be 7.
Okay. Yeah.
Okay. Okay. How did you get on
that
with
question as well? Would you just need to do 3 points and
3 points?
Yeah.
Yeah. So did you get those 3 points?
Yep. So there's 4. For starters, there's 4 protons, 3 neutron.
Good.
All the mass is concentrated. No, sorry, 3 protons, 4 neutrons. And then all the mass is concentrated in the nucleus.
Good.
Because the electrons have near to zero mass, and
Good.
the
Well
protons
done.
have 1. And
Good.
then the third one is the third one.
So what's the third point? It says explain in terms of subatomic particles. So you're talking in terms of subatomic particles because it says in terms of protons, neutrons, and electrons. Yeah. So you've already made the point on talking to say the mass of an atom is mostly concentrated in the nucleus, number 1. Number 2, protons and neutrons live in the nucleus.
Okay. So
they have a relative mass of 1, whereas electrons have a mass of nearly 0.
Okay.
The mass is concentrated in the nucleus. The nucleus contains protons and neutrons. And each have a relative mass of 1.
I'm sorry.
A relative mass of 1, whereas that of an electron is nearly 0. Okay, and lithium has 3 protons. The next point. Lithium has 3 protons and 4 neutrons.
Okay.
Giving it a mass number of 7. Okay, good stuff.
Then the next question was,
Yeah.
oh, I didn't get B or C. I didn't get B or C.
Okay.
So amount of
Amounts of
substance.
substance can be described in different ways. All right. So one mole of a substance is the relative formula mass in what could that be?
I know what a mole is, but I didn't get what this.
So what formula do we use?
Mole equals to mass divided by relative formula mass.
Okay. So if you want to get 1 mole, yes?
Yeah.
if you want to get a value of 1 mole, what mass would you need? What would the mass have to be equivalent to?
The relative formula mass.
It would have to be equal to the relative formula mass, wouldn't it?
Yeah. So 1 mole of something is the relative formula mass in.
How do you describe that? Have a little think about that one.
Okay.
They haven't given you any options, have they?
No.
No? Okay. So 1 mole of a substance is the relative formula mass in 1 gram? No, it can't be 1 gram.
No.
It's a cheeky question, isn't it? So 1 mole of a substance is the relative formula mass in Now, what they've said here, actually, they're giving you the choice here, Jay. You don't just have to think of 1 word. You could actually write a sentence if you wanted to.
Okay, so
The 1 mole of a substance is the relative formula mass
is it like in the periodic table? Because like the relative.
Okay, in the periodic table, yes, but you sort of right there. But what's the value of the mass? What unit is the mass in?
Grams.
Well done.
Oh, is it? It's just grams. I was gonna say that, but then I was thinking you don't really measure the relative formula mass. You don't put like a unit next to it. So.
Yeah, but normally, did you remember the first question we did when I said how many moles of sodium chloride are there in 50 grams?
Oh, okay. Yeah.
Yeah.
So would it just
Tricky
be
one, it's
one?
a cheeky one.
Yeah.
1 mole of a substance is a relative formula mass in grams. Because then that one is in grams, and then you divide by the relative formula mass, then you will get 1 mole.
Okay.
Okay. Now, the relative atomic mass of an element compares the mass of an atom of an element with the mass of an atom of, what's that one going to be in there?
So the relative atomic mass of an element compares the mass of an element
with a mass of an atom of what?
Is it hydrogen? Because it's 1 1.
Yeah, it almost feels like it should be hydrogen, doesn't it? Yeah. But for this one, and it's one of those which will crop up every now and again. They don't throw them in regularly, but just as well, you see it. But worth remembering. So they compare it with the mass of an atom of carbon-12.
Carbon, why 12? Carbon 12.
Carbon-12, the reason why is because carbon has different isotopes. You've got carbon-14, which if you remember is radioactive and is used for carbon dating. So you've got different isotopes of carbon, so we use carbon-12.
Okay.
Just carbon-12 that was selected and everything was made relative to it. Okay? So when you write carbon-12, you write a C with a little 12 next to it as a little superscript at the top. I could have shown it to you if I could share my screen, but I could show it to you later. Or you can just write carbon-12 with a dash and then 12. Yep, that's it.
Yeah.
Mass of an atom of carbon-12. Okay.
And then which other ones? I think it was 4A, but I got the second part to it, but not the.
Okay, so if you scroll down, then I'll be able to see that.
It's this one here.
Okay, so 4A, copper is a good conductor of electricity. Explain why. Okay, what attempted you? How do you approach that question, Jay?
Well, I was trying to think of delocalized electrons.
Well done. You're on the right track. You're on the right track. That's a key word there. So delocalized electrons. So you want to say
So
that copper has metallic bonding.
wait, what is metallic? Is it that just metal bond?
Yes, absolutely. So it's the type of bonding that is exhibited in metals.
Oh,
So
okay.
metals have got these positive ions that are fixed in a lattice. And that is why metals then have a fixed shape,
Yeah.
so to speak. But also between those positive ions is this sea of mobile electrons.
Yeah. Is that the delocalized?
Those are the delocalized electrons. And for conduction of electricity to take place, you need mobile electrons within the bulk of the material.
Okay.
Copper has got a high density of these mobile electrons, which makes it a good conductor.
Okay. Yeah. Right.
Okay? So in copper, there is metallic bonding, i.e. positive ions surrounded by a sea of delocalized electrons.
There is metallic bonding, and there's a.
Yeah. So you have got. So yeah, you can write i.e. meaning that there you have positive ions
That they have.
positive ions in a fixed lattice surrounded by a sea.
Sorry, say that again.
Surrounded
by
yeah,
high density.
yeah, surrounded by high density of delocalized electrons. Of delocalized electrons.
Electrons. Here.
Okay. And then of course you might run out of space to write this, but you might then just put to say conduction of electricity depends on the presence of delocalized electrons.
Okay.
Conduction depends on the presence of delocalized.
Conduction depends
on the presence of delocalized electrons. So you got the 2 points there, okay?
Yeah.
Good.
And then I got BI, and then I think.
You okay with that one? Calculate the maximum mass?
Yeah.
Okay.
And then I think it was the next one 5.
Yeah.
Yep, I got it all, the rest of it.
You were okay with that one then, were you?
AI.
That 5 AI?
No, I didn't get that one. I didn't get 5 AI. That's the next one. Yeah.
Okay. So the hydrogen produced was collected. Describe how to test this gas to show that it is hydrogen. Can you remember how to test for hydrogen?
Is it you put something on top and then it makes a squeaky pop sound?
Yeah, so you bring a burning splint.
Yeah, burning splint, that's it. And
yeah, you use a burning splint and it puts it out with a squeaky pop.
Yeah.
Okay, so test, bring a burning splint to the gas. Result, the burning splint should go off with a squeaky pop.
Yeah.
Okay. And obviously what's happening there is that the burning splint is just providing activation energy for a reaction to take place between hydrogen and oxygen. So when you hear that squeaky pop, hydrogen has combined with oxygen and water has been formed.
Okay.
And that's why it puts it off, because the water itself puts out the fire.
Yeah, yeah, okay. So
Okay.
all it is burning splint with a bit of fire on it, and then
Yeah, that's it, burning splint. And the other test that they'll want you to know as well is that of oxygen. Can you remember the test for oxygen?
oxygen. Um, Not really, but
Not
could they?
really. That one, it reignites a smoldering splint.
So
So if your
reignites.
splint is smoldering,
Yeah.
yeah, so it's not on fire, you can't see the flame, and you put it into a jar of oxygen, you then get a flame produced.
Yeah, I was about to think. I was trying to think before because I know that it only can happen with it because it reacts with the oxygen. So
Absolutely. So it actually burns more because it's got extra fuel. So you should see a bigger flame. So it reignites a smoldering splint.
okay, yeah,
Okay. So those are worth remembering. That of hydrogen, they're not so easy to forget, hopefully, because they're all using a splint. In one case for the hydrogen, it's burning, whereas for the other one, it's smoldering, and you're expecting to see a bigger flame, or you're expecting to see it reignited.
yeah.
Okay.
Okay.
Good stuff. Good stuff. So went for 5AII. You okay with
Yeah.
that one, hopefully?
Um. No, I don't think I got that one right. No, I didn't get that one.
Okay.
No.
Explain why the magnesium has to be heated. Any ideas why you think the magnesium would have to be heated?
Is it for activation energy?
Absolutely, yeah. So it provides an
Um.
activation energy. You're absolutely right, which then allows the reaction to take place or increases the kinetic energy of the reactants such that they can then collide successfully and produce products.
Yeah. Okay. And then so it increases the kinetic energy, so they can.
Yeah, you could also talk about that, because what they're going to be assessing is your understanding of kinetic theory, in that before a reaction can take place, the reactants need to collide, but they need to
Yeah.
collide with the right amount of energy, which is greater than the activation energy. And also they have to have the right orientation,
Yeah.
yeah, so that that collision can happen. And only when a successful collision happens, only then do you then see the product, so to speak.
Yeah.
Okay.
Yeah. Okay. Yeah. Got it now.
Okay,
Uh,
great stuff.
and then BI I got. So the next one is
Yeah.
I got BI, and then I got
Okay with
BI.
that one. Good.
Yep, I did those three. Yeah.
Okay, and the percentage yield, you were okay with that one, weren't you?
Yep, I said
134.5.
some of the reactants may react in different ways to the expected reaction, so we do not get the product we expected.
Yeah, very good, very good. That is spot on. That is absolutely spot on. Good stuff. Okay, great. At least now you've attempted this, I'll look to sending you that full mark scheme as well, Jay. And if there's
Yeah,
any
yeah.
other things that you just want to counter check your calculations, then you have it as well.
Okay.
Well done for the good work. Good stuff.
Yes.
Is that another set of questions?
No, that was what I was doing before,
That's what
but
you
then,
focused on. No
yeah, I was doing that
problems.
before, but then I did something wrong, so I had to do it again. I just had it behind.
No problem. Okay, very good, Jay. Keep that up. Keep bringing as many questions as you can.
Okay. All right, do
Um,
you want me to stop sharing so that you can
okay,
use
cool.
your? Yeah. Ah, there you go.
All right, perfect. Righty. So we are going to be looking at something slightly new today. Where's my board? Here we go. All right. And what we're going to be looking at then, Jay, we're going to be moving on then, still looking at concentrations and things like that. But we're
Yeah.
going to be looking at it with a slightly different twist. I'm just looking for my, there we go. Ever heard of this word, titration?
No, no.
No. Okay. It's a pretty powerful technique in chemistry that we use if we want to determine the concentration of an unknown liquid, so to speak. Okay. So,
Yeah.
say for instance, and I'll put that there. Say for instance, I had a known concentration and a known volume of an acid, and I wanted to find out what the concentration of a particular base was. Well, I could do a bit of a reaction between the acid and the base, or the alkali. So can you remember, firstly, what are the products when you react an acid with a base, or indeed an alkali? Can you remember what you get?
Is it? I think you get water,
You definitely get water, good.
and then is it a salt?
You're absolutely right.
Okay.
Okay. And we have a
Yeah.
name for this type of reaction. Do you know the name of what we call such a reaction?
Um,
Starts with N.
Starts with M. Sorry.
N?
M. Okay.
Any
Is it a
ideas?
neutral reaction?
Absolutely, nearly there. We call it neutralization.
Oh, neutralization. Okay.
Okay? So we talk about the reaction. It's that reaction.
Okay. Yeah.
Why do we call it a neutralization reaction? Any ideas, Jay?
Because it makes it neutral.
Yeah. What does it make neutral? What was not neutral and what has been made neutral?
Well, it's an acid and an alkali, so they're both different pHs. So they're on
Different
the
pHs. They're almost at the polar ends, isn't it? So for this one, we're expecting a pH that's less than 7. Yeah.
yeah.
And for this one, we're expecting a pH that is greater than 7. Yeah.
Yeah.
And then when we combine them, what do we get? We get a pH that is equal to 7.
Okay. Yeah.
Yeah. So we've come from both ends and come and combined at a neutral. And pH 7 is what we call a neutral pH. It is neither acidic
Yeah.
nor alkali. All right. Good stuff.
Is a base just an alkali?
Yeah, indeed. A base is just an alkali that, a base is an alkali, if you like. I'm using the word alkali. It's one
Yeah.
that you have not dissolved in water. In other words, a metal oxide.
Okay.
So if I gave you an option of, so you've got sodium hydroxide and sodium oxide.
Yeah.
So this here is a base. That here is an alkali.
Okay.
Okay.
Yeah.
If I dissolve this sodium oxide in water, it's going to form this sodium hydroxide. So I no longer have a base, I now have an alkali.
It's gonna dissolve with the hydrogen and then.
Yeah, you can write so this plus H2O, what's this going to give me? It's going to give me sodium hydroxide.
Yeah.
Okay. Now, of course,
Yeah.
we can try and balance this equation by putting a 2, I believe. It's balanced.
Yeah. Yeah. That's it,
Okay.
yeah.
So I've gone from a base to an alkali. So far, so good. Great stuff. Now, key thing as well is to be able to balance equations with both acids, with bases or alkalis, but that's not a problem because you can do it. But for the major purpose, when you do titration, it would normally be an alkali that you will be using, Jay, as opposed to a base.
Yeah.
Okay?
Yeah.
So, normally I'll have, say I might be wanting to find the concentration of the acid. So somebody has given me a jar and said, right, here we go. We've got some acid in here and we want to find out the concentration of that acid. The first thing I need to know, so question is, what is the concentration? And we have an acid. The first thing I need to know, firstly, to help me is I need to know what type of acid it is.
Yeah. Okay.
And I also need to know, because once I know the acid, then I can identify what alkali I'm going to react it with, and I can write out a balanced chemical equation. So unless I know what the acid is, I cannot write a balanced chemical equation. So I need to know that. That is absolutely paramount.
Yeah.
What I then do is, once I know that acid, So let's imagine that now I've been told to say, right, the acid is actually hydrochloric acid. We're given that now. Great. But we still don't know its concentration. And that's what we're trying to do. Okay?
Yeah.
So what I do then is I get, if you like, a known concentration of sodium hydroxide. So this is my alkaline. And I've got a known concentration. So known concentration and volume. Of this sodium hydroxide. Now we're going to use just as an, well, we're going to just use as an example. So I'm going to have 25 centimeter cubed, and the concentration of my sodium hydroxide, shall we say, will be 0.1 mole per decimeter cubed. So I've got a known volume of it, and I've also got a known concentration of it. Okay. You happy with that?
Yeah.
Okay, great stuff. What I then do is I take, and to get this non-volume, I could use some pieces of kit. There's something known, if I want to be very accurate in terms of the volume, I could use something known as a pipette. Now, you have seen pipettes in your lab, I hope.
Yeah, there's squeezy things in there.
Yeah, you've got the squeezy ones, but you've also got the more accurate ones where look something like that, and you put your finger at the top, and you literally, or you can draw, you've got a syringe which you use to draw a fixed amount to a certain level. All right. These are more accurate than the ones which have a little bulb at the end which you kind of squeeze. Okay. So these are a certain pipette that is used specifically for titrations. Okay.
Yeah, I've never used that one before.
No, I don't think you've used that one. I don't think you'll use it probably until at least well into year 10, if not year 11.
Yeah. Okay.
Okay. Right. So now I've got my non-concentration. I've also got my volume. All right. Now this is the little bit of the, it's a bit trickier in terms of the calculations when we come to it, but just follow what I'm trying to, the overall picture I'm trying to give you. And then when we get to the calculations, we'll hopefully would have had a good foundation to understand what's going on. So the next thing I do now is I use a burette. Now in this burette, I pour in this acid. Now, what I also need in here is I need to put what is known as an indicator. So there's a number of indicators that you can use. The reason why I'm going to be using an indicator is, any ideas why I might be using an indicator? Remember, this is the acid here, and I'm going to be adding it in, and I'm going to add it until a neutralization reaction has happened, and the reaction and all the sodium hydroxide has been used.
Yeah,
yeah, go for it.
Because you put a neutral the indicator in to find out the pH, because it's like comes up with a color, and then you see
you're absolutely right. So I'll use an indicator to firstly verify that I'm using sodium hydroxide. So it will come up with a color, but I will then start adding this acid, which I know is hydrochloric acid. And as I add it to the sodium hydroxide, a certain reaction is going to happen. Well, what's that reaction going to look like?
It's going to be the acid plus the base, which is going to make a water. And so it's
going to form H2O plus NaCl. This is the reaction that's going to be happening. Okay? So I'm going to use a type of indicator in here. Now, common indicators that you need to be aware of are, firstly, we have something known as phenolphthalein or phenolphthalein. Ever heard of that indicator, Jay?
No.
Okay. It's colorless in acid, so you need to remember this. But it's pink in an alkali solution. So I choose an indicator such as phenolphthalein. We've also got another indicator, if I take this off here, called methyl orange. Have you heard of methyl orange?
No, we've never really like learnt the names of it. We've just known it's an indicator in them.
Okay, so these are names worth remembering here.
Okay.
Worth remembering. So that's an indicator. Now with methyl orange, this is red.
Red. Okay.
Acid.
And then the other one's color. Yeah. Colorless.
So red in acid and yellow in alkali.
Okay.
So you can use any of these. You've also got another one, litmus, which you can use as well. Litmus is blue in base, but red in acid. You probably have used litmus paper. Yeah. And there's another one called universal indicator. Do you remember?
Yeah, that's what we've been using here, universal indicator.
Yeah. Now, universal indicator is not the best to use for these types of experiments. Okay. And the reason why is, as you add this acid, so you're going to look at your starting point. Where does my volume start at? And you're going to add this acid to this alkali very slowly in drops. So imagine you're using a phenolphthalein indicator. It's going to be pink to start with. As you add the acid, the moment all the sodium hydroxide gets used up, and you then have a next drop of acid, that acid would make that indicator turn colorless. Because now you've got excess acid. Because look at the reaction. As the sodium hydroxide is used up, eventually all you're going to have in that vessel, okay, is going to be water and sodium chloride. Are you following me so far?
Yeah, yeah.
Okay. So once all the sodium hydroxide has been used up, all I have is water and sodium chloride. The moment I then add an extra drop of acid, that is going to change it from pink to colorless. And at that point, I know that all the sodium hydroxide has reacted, and I call that point, I call it an end point. So I'm looking for an end point. And now let's imagine that my volume is there. That's my finishing point.
And you measure that?
Absolutely. Then I measure what, now I ask myself, well, what volume of acid did I use? Now let's imagine, for argument's sake here, let's imagine for argument's sake that I used 30 centimeter cubed. For argument's sake. So far, you're following me? I got to the end point, the phenolphthalein went from pink to colorless, and I knew, right, stop there. I closed my burette, and I know the volume I've used is 30 centimeter cubed. Now I go to my formula, and I look at the ratio of moles. In this equation is balanced. I hope it is. Looks like it is.
Yeah.
You can see that 1 mole of sodium hydroxide reacts with
1 mole
of HCl. Good.
Yeah.
Now I ask myself, well, how many moles of sodium hydroxide did I have? I know it's 25 centimeter cubed, and I know the concentration is 0.1 decimeter cubed. Can I calculate the number of moles of the sodium hydroxide that I had in this solution?
Yeah, you can do the concentration equation, which is
good. Well done, Jay. Good for so if I want to work out moles, it'll be concentration times
volume.
Hold on.
So the concentration is 25, and then the volume.
The volume is 25.
The volume is 25, sorry. And then
concentration is 0.1 per decimeter cubed.
Yeah.
So what am I going to do with that?
So 25 times 0.1.
Yeah, it's tempting to, but remember, this is in centimeter cubed. Well, this is in decimeter cubed, so don't get caught out. You need the same unit here.
Okay, so
what should I change that to?
You go 2 to the left, so 0.25.
0.25, not quite. If something is in centimeter cubed, to change it to decimeter cubed, I divide by what number?
10.
Not quite. By 1,000.
Oh,
Remember, it's 10 cubed. 10 times 10 times 10. So I divide 25 by 1,000.
okay.
Yeah.
So 0.025.
0.025, correct.
Yeah.
And I'm going to multiply this with 0.01 moles. Yeah. Per decimeter cube. And how many moles of sodium hydroxide does that give me as?
2.5 times 10 to the minus 4.
Okay, so I get 2.5 times 10 to the minus 4 moles. So I know that when I'd finished and I'd used 30 centimeter cubed, yes?
Yeah.
2.5 times 10 to the minus 4 moles has to also react with 2.5 times 10 to the minus 4 moles of
Hydrogen chloride,
hydrochloric
because
acid. Well done. It has to, because the ratio is 1 to 1. So I know, therefore, that in 30 centimeter cubed of the acid, there was actually 2.5 times 10 to the minus 4 moles of the hydrochloric acid. So now I can work out the concentration of the hydrochloric acid by what? By using this formula, moles divided by volume. So my moles this time are 2.5 times 10 to the minus 4. I divide that by the volume of use is 30 centimeter cubed. So I'm using that formula.
yeah.
So 30 divided by 1,000, what does that give me?
0.03.
Okay. And now I can work out the concentration of this acid, because that is what I'm trying to get. So I get 2.5 exponential minus 4 divided by 0.03. And that gives me a concentration of this acid as 0.008 moles per decimeter. Are you happy with that, Jay?
Yeah.
Okay.
Yeah.
A lot going on here, but if you kind of trace it, the concepts are we're still using the ratio of moles from the equation.
Yeah, you're still in, because it's the same. If it's 1 to 1, then it applies to the.
Exactly. But now we've incorporated that moles with that formula as well.
Yeah.
Yeah, good stuff. Right. Some heavy going there, Jay. So what I'll suggest is we take a break, and then when we get back, we have another closer look at some worked examples, just to bring it more to life for you.
Yeah. Okay.
Great stuff. So I now make it to be 11:30. If we meet up at about 11:35.
11:35. Right. That's good. Yeah.
Good stuff. See you shortly then, Jay.
Cheers.
Nice one. Fantastic. Welcome back, Jay. Nice one. So we are going to look at some questions here. Let's go there. Okay, we could look at, tell you what we'll use. We'll use this one, titration calculations. This is just examples. Okay, and I'll blow this up. All right, so let's look at this one here, Jay. Yeah, as an example. I'll tell you what we do to make life easy. I will bring my screen by next slide to it. Okay, no, you can't see my screen yet. Okay, that's better.
Yeah.
Great. All right, so it says in a titration, 25 centimeter cubed of 0.1 reacted with 30 centimeter cubed. Oh, good heavens, this looks exactly like the one we've just done. I didn't even know. I really didn't know that there was this question that existed. But there we go. Right, let's have a go at the next one then. 63. In a titration, 25 centimeter cubed of potassium hydroxide solution reacted with 27.5 centimeter cubed of 0.5 moles sulfuric acid. Find the concentration of the potassium hydroxide in moles per decimeter cubed. Give your answer to 3 significant figures. Okay, so they've given us a reaction there, and I think they've been kind enough as to balance that equation for us as well.
Yeah.
So we've got that balanced, and we are going to need this. So we do need it balanced. K2SO4 plus 2H2O. Okay?
Yeah.
All right. Now, what are we told? We are told we're given this here. They've given us some values of concentration and volume. We know the volume is 27.5 centimeter cubed, and we know that the concentration is 0.5 moles per decimeter cubed. And they've asked us to work out the concentration of this guy here. Do we know the volume that was used? Yes, the volume apparently is 25.0 centimeter cubed. So far, so good?
Yeah.
All right, great stuff. Now we need to ask ourselves and say, well, of this sulfuric acid, how many moles of it were used? What formula do you reckon we're going to use if we want to work out the number of moles of sulfuric acid that were used?
Concentration equation.
Yeah, okay, so we're going to go to our concentration equation. What does that state? It tells us that concentration in moles per decimeter cubed is given by the solid in moles divided by the volume. And this volume, let's not be caught out, must be in decimeter cubed as well.
Yeah. Okay.
Okay, so we rearrange our formula to work out the number of moles of sulfuric acid. So how do I rearrange? What does that become if I rearrange it?
Concentration times the volume.
Well done, good. Okay, that goes upstairs. So it's concentration times volume. All right. Now, what is my concentration? 0.5 moles. Yeah, and it's given to 3 sig figs as well. So I should keep that in mind. And it says I should give you answer to 3 significant figures. If it doesn't, look at the number of significant figures of the largest unit given and work to that if you're ever in an exam, if they haven't specified, okay? So times the volume. What's the volume? What value for volume am I going to use here now, Jay?
Would you use the you use 27.5?
Okay, what do I need to do with that though? Because remember, I rearranged this. Sorry?
Yeah. You need to divide it by 1,000.
You're spot on.
0.
Divide it by 1,000.
0.0275.
Yep, okay. Times 0.5. That gives me what value? 0.01375.
Okay.
So these are the number of moles of the sulfuric acid. Are you happy?
Yeah, yeah.
Because I've used the volume of the sulfuric acid times by the concentration.
Yeah, it makes sense. Yeah.
Okay, great stuff. So how many moles would this sulfuric acid need to react with so that we get this neutralization reaction? How many moles?
Well, it's all 1-to-1.
Is it 1-to-1? Be very careful. What's the ratio?
Oh, that's 2, sorry. That's a 2, and then the other one's a 1.
Okay. So I'm not really too bothered about this side of things because I'm really just interested in that. So I know the number of moles. Yep. So what would the number of moles of sulfuric acid be?
Double 0.01375.
Correct. Yeah, I meant potassium hydroxide. Sorry. So moles KOH therefore equal to 0.01375 times by 2. I've used that ratio. Absolutely spot on. Times 2. And that gives me
0.0275.
correct. Now I know the moles.
Mm-hmm.
And I also know what else do I know? I know the volume that was used.
So then you just put it back into the equation.
0.0275. Now this, I'm using this formula now, divided by the volume. What's the value for the volume I'm going to use, Jay?
0.025.
Very good. So I'm going to divide that to 0.025. Okay. And what does that give us?
0.025. It gives you 1.1.
1.1. Yeah.
Mm-hmm.
Now the 1 to 3 sig figs, Jay. So
Okay.
is that just 3 sig figs?
Would it be 1.10?
1.10. Okay.
Yeah.
And it's a concentration. So I've got to remember to include my units. Yeah.
Yeah, fine. Yeah.
Really happy with that? Good.
Yeah.
Now let's have a go. Your turn to have a go at number 64, Jay. Number 64. You're doing number 64, Jay?
Oh, sorry. Sorry.
No problem.
Na 2 CO2 plus H2O. Okay. And then we just need to make sure it's balanced.
Yep.
2 NAs, 2 NAs. Yep, and it's balanced. So
Good.
okay, so now you know that the sodium carbonate is 20 centimeters. 20 centimeters cubed. That's the
Good.
volume. And then reacted with 24.1
Good.
centimeters cubed of 0.4 moles.
Good.
Of hydrochloric acid. Find the concentration of the sodium sodium carbonate solution in moles per decimeter cubed. Grams per decimeter cubed. So is that the sodium carbonate is this one? So okay,
Yep.
so what we need to do is we use this equation, that one,
Well done.
and then we rearrange it so that you're doing volume times by concentration.
Good man. Good.
So yeah, so 0.4. Yeah,
Good.
0.4
Good.
times by 0.0241,
Okay. Good. Good.
and then 241, and you get 9.64 times 10 to the minus 3.
Good.
And then once you've got that, the ratio is 2 to 1.
Good.
And then, so you're going to half this.
Good.
Divided by 2, which gives you 4.82 times 10 to the minus 3. And now you put it back into the equation.
Good.
And then answer the contrary, so you put it back into the equation. So that's your moles times by the volume. No, divide by the volume, which
Well
is
done.
24. And then you get 2.41, but they give me in standard form. So
Now just be very aware then, Jay, when you said moles, the 4.823, and you divide it by volume, don't get caught out. If the volume is in centimeter cubed, you've got to change it to decimeter cubed.
okay.
Okay.
So 0.02.
Okay, good.
And then if I do it again, so point times 10 to the minus 3. And then that divided by 0.02.
Yeah.
And this time it gives you 0.241. And this one's moles per decimeters cubed.
Excellent. Good. Well done.
And then it asks the final concentration in moles. So do you have to give it in the grams per decimeter cubed as well?
It wants it both in both moles per decimeter cube, which you've done, but it also wants it in grams per decimeter cube now.
Okay, so if I just write this 0.24 cube, and then that's the 3 significant figures as well. So
Okay.
now they want it in grams, so
Yeah.
you do you want to convert the moles into grams. So if we know this is the mole,
Yeah.
2 times 10 to the minus 3, if that is the mole, then can't you just use the mole equals to mass divided by m1?
Yeah. Good. Keep going. You're doing good.
Okay, so mole, so we want to look at the mass, so if you bring it there, so that's mole equals to the mass. So our relative formula mass of sodium carbonate.
Good stuff.
The sodium's 23.
Yeah. Good.
So
That's much better. Excellent. No worries.
23.
Yeah.
And then our carbon, I think it's 12.
Well done.
Yeah,
Good.
and then our oxygen is 16.
Good.
Okay, and then we do 223, so 46
Yeah.
plus 12 plus 48 and plus 48, and you get 46, 12, you get 106, and then so we know this is 106, and then 106 times by 4.82 times 10 to the minus 3. So if I just convert, so 20 times 106. Is this the 4,820 same as the 4.82 times 10 to the
No,
minus?
4.82 times 10 to the minus 3. If it was 4.82 times 10 to the power of 3, then you're right. It would be 4820, but it's to the minus 3. So the decimal is going to the left side of that 4.
Yeah.
Moving that decimal point 3 places. Good.
And then that times now by 106. Um, 0.5109. So we get point. No, we don't need to. So 0.5109. And then now we've got that, we divide it by 0.02.
Okay. Uh, 0.02 as opposed to 0.2, I think.
Yeah, 0.02, sorry.
Okay.
Yeah. 25.546, and then 3 sig fig, it's 25.5
Okay.
grams per decimeter cubed.
Now, the slight drawback, you've absolutely got to the right answer. Well done.
Yeah.
You used a slightly longer route, another route you could have approached it from. So what did you get as your concentration in moles per decimeter cubed again, Jay? In moles
Sorry,
per decimeter
yeah,
cubed. Yeah, in
moles
moles per decimeter cubed. What was it again?
0.241 moles per decimeter cubed.
0.241 moles per decimeter cubed. Good. Now at this stage, if you know the moles per decimeter cubed, you now just need to change this moles into grams. So you could have simply said, well, I'm going to multiply this 0.241 by the relative formula mass of sodium hydroxide found as 106. That would still be under decimeter cubed. Because all you've done is now change these moles at the top, change them to grams. And obviously, you know the formula you're using here is that mass is equal to moles times the relative formula mass, which is what you're getting here. So that's the moles, and that's the relative formula mass. Now, if you do that, you get 0.241 times 106, and the answer comes out right away as 25.5 grams per decimeter cubed.
What you need to do is just change that moles bit to
That's it.
grams using the equation, and then you're done.
You're done. And again, it shows understanding the fact that you decided to go down the other route where you ask yourself, well, how many moles do I actually have of this thing? What mass does it represent? And in what volume was it? So you still went back to that 20 centimeter cubed to then get the answer. So you got there in the end. Well done. Well done. Another one for good measure here. I might have to, however, reduce this now. Does that make it hard for you to see?
No, it's pretty clear.
Number 65, citric acid is found in many fruits and juices. A titration was carried out to find the concentration of a solution of citric acid. Well, this is where the main bulk of the question is. Over here. Yeah. So they want to find out the concentration of a solution of citric acid. 25 centimeter cubed of the citric acid solution was reacted with 35.5 centimeter cube of 0.05 moles per decimeter cube sodium hydroxide. Calculate the concentration of the citric acid in moles per decimeter cube. In the equation below, the citric acid is represented by H3A. Give your answer to 3 sig figs.
Okay. I'm sorry, I keep forgetting. Okay, let me just check this balance. So 3 hydrogens, 4 hydrogens, 6 hydrogens. So yep, oh sorry, it is balanced, yeah. Okay,
Okay, good.
and then okay, and then
Good. Fantastic.
okay, and then just do the volume times that.
Yeah,
0.0335. 35 times 0.05. Okay, so now that's the moles of
yep.
this, and then there's a 3-to-1 ratio,
Good, well done.
and then so we divide this by 3.
Well done, good.
Yeah, if I do on that next page, so 1
No
point.
problem.
Let me check first. Yeah, and then we divide all this by 3.
Yeah,
So 0.0005, and then so now that's the moles for the citric acid.
good, well
So
done.
citric acid, and then all we do is, we know that was the volume. So we do this, the answer we got divided by 0.025.
Top man.
25, and then get 0.0223 recurrent, and then that is our moles per decimeters cubed. And then give your answer to 3 significant figures. So 1, 2, 3, and if you add another 3, and then it would stay as
0.0223 moles per decimeter cubed.
yeah.
Well done. Brilliant. So what we're going to do then now, Jay, is actually look at actual exam questions, so you can have a feel for what they look like when they appear in your exam. Here we go. Okay, we can have a look at these. So again, this is under acid. So some of these questions are a little bit unfair, but we might as well have a brief discussion. We will look at them in more detail nonetheless when we start looking at acids and bases. And I think we may have covered a little bit of it. So whatever you can remember, see if you can remember. But I know that it may be a bit of a long shot. But here it says sulfuric acid is a strong acid. What is meant by a strong acid? Any ideas?
Is a strong acid like a really low pH acid, like a 1, 2?
Yeah, low pH acid, you're right. So they have very low pH, but also there's something that you want to speak about. We say that an acid is a proton donor. That's what an acid is. Yeah.
Yeah.
And a strong acid is one that is fully ionized. So all the proton, the hydrogens are fully ionized in water. That is what we mean by strong acid. It says write the equation for this neutralization reaction. Now, would you be in a position to write an ionic equation for a neutralization reaction?
Isn't it just the ions? Because do you know how you say it was ionized as well? Does that mean it's radioactive?
No, actually. So when we talk about fully ionized, so it's essentially ionization is not the same as radiation. So ionization is all to do with the loss of electrons. Okay. Whereas radiation is to do with stuff coming from the nucleus of an atom. Okay, so for something to be ionized, it has either gained or lost an electron, which has nothing to do with the nucleus. So whereas radioactivity is to do with the nucleus itself.
Yeah, because it's the protons.
Yeah, but I know you're coming back to something we spoke about when I was saying how ionization can, radiation or radioactivity can lead to ionization, which in turn can lead to, if you like, the buildup of an acidic environment. In some of the ways it can damage your body indirectly. That is what you were probably referring to, because we did have a little discussion on this. I remember when we were looking, when we were discussing radiation in physics. So good for bringing those on board as well, just so you can really clearly see the picture. But no, there is a difference, Jay, between ionization and radiation. I hope it makes sense in terms of how I've explained it.
Yeah. So if you're going to write the ionic equation, would it be?
Yeah. No, we haven't looked at this. I doubt we've really looked at this, but I can give you a little hint on it so that when you do have it, it's not completely new territory. But we will do it when we start looking at acids and alkalis in more detail. Na2 SO4 plus 2H2O. So now here we can write these, instead of writing this chemical equation, we can write it in terms of ions. So what ions are present? So first, the key thing to note is that every alkali has this hydroxide ion. Okay? If it is from group 1 or group 2. Okay, and if it's a hydroxide, it will have that there. So I can rewrite this in terms of its ions. So the ions that make sodium hydroxide are composed of Na plus and of a hydroxide ion.
Okay, yeah.
Okay. The ions that make up sulfuric acid, well, this is also an ion. It's a sulfate ion, and it's got that charge there.
Yeah.
Okay. Now, because this is an acid, it's got H pluses or proton donors. In other words, it's got hydrogen atoms that have lost an electron. So looking at this here, I have got 2 hydrogen atoms that have lost an electron. So I've got 2 H plus. Because every hydrogen that loses 1 electron has an extra simply, or in other words, it's just a protein that is positively charged. So that's what's that representing. This here is representing that this is 2 negative, it's got 2 negative charges on it.
Yeah.
Key thing to note is that these charges must always balance, must always add up to 0.
Okay.
Because it's as it is, it's not a charge. Sodium hydroxide is not charged. If you put your hand in it, there's no charge. You're not going to get an electric shock. So in other words, it's neutral. Same with the sulfuric acid. The 2 positives are balanced by the 2 negatives. So again, this is, if you like, neutrally charged. It's got 0 charge overall. But these are the ions that are inside it. So what we're writing here are the ions inside it, and hence why they call it an ionic equation. Same here.
But also, no, actually, yeah, it makes sense. So I was just thinking.
And yes, the overall charge this side will be equal to the overall charge that side. So there we go. Again, I've got this SO42 minus. But whatever, this is not made of ions. This is a molecule. So I can't write this as ions. I have to write this as a molecule. So far, so good?
Yeah, so that just has no charge, it's just stay.
Yeah, there's no charge because water is covalently bonded.
Ah, yeah, it's not ionically bonded.
It's not an ion, you're right. That's a molecule. This is an ion because this is to do with transfer of electrons. Again, electrons are transferred here and electrons are transferred in there.
Well, is the H2O is sharing the electron.
Correct, you're absolutely right. So now the next thing is what I do is I cross out what appears on both the left-hand side and the right-hand side. So here, hopefully you can see that these 2 sodiums cross out with these 2 sodiums here.
Yeah.
Yeah, good. This SO42 minus here, really be crossing them from here, really. So I've got 2 sodium which I've crossed out, which leaves me with 2 OH, because this 2 multiplies to everything.
Yeah.
Okay, good. Now I can cross out my SO42 minus on the right-hand side and cross that out as well. So what I remain with now on this side, Jay, hopefully you can see that, I only remain with my this here, and this here. The rest of the stuff has been crossed out. So the ionic equation, or the shortened version of what's going on in this reaction, is that 2 hydrogen ions are being accepted by 2 hydroxide ions, which then form water. And this is the equation they're looking for.
Yeah.
Okay. Again, we'll look into more details of how to write these equations. Yeah, go on if you've got a question.
No, I was just saying it sort of makes sense, but like I kind of lost a bit with it.
I know, and it would be, I'd need a whole session, a whole lesson just to go through writing ionic equations, okay? And it's I've tried to squeeze or compress a whole lesson into 5 minutes of me talking about it. But the key points I want you to take is that to find out the ionic equation, break down the reactants into ions as well as the product. That is, if that thing exists as an ionic compound. If it doesn't, leave it as it is.
Yeah, so you break it down, but how do you know what the charge is on it?
Okay, the charges are easy to know because the charges are all related to what group they are in the periodic table. So is in group 1, it can only form a +1 charge.
Yeah, and then in the group two, I think it's a -1, I think.
Yeah, sorry. Hydrogen as well, it's also only got, it's effectively in group one, hydrogen
Yeah.
is. So again, it can only form a +1 charge. If I had a different metal, like say calcium hydroxide, calcium hydroxide is in group two. So if I had to write this in terms of its ions, it would be Ca2 plus. Calcium loses 2 electrons always.
Oh, okay, okay. Yeah.
And those 2 electrons would each be received, one of each would be received by a hydroxide ion.
Yeah, to make it balanced. So
Yeah, so
neutral.
there's 2 negative charges and 2 positive charges. When you add them, 2 minus 2 is 0. So this has got an overcharge of 0.
Yeah. So, but do you know how it needs 2 electrons to make it stable? The calcium.
Calcium needs to lose 2 electrons.
Oh, sorry, it needs to lose 2 electrons.
Yeah.
How does it? How does the? Do you know the oxygen and the hydrogen? How does it give its electrons? Like which one gives which what?
So this hydroxide is an
Yeah.
ion that exists. So it's not so there are a few ions that you need to know about. So you've got the nitrate ion, you've got the sulfate ion, and their
Yeah.
charges. Okay, so these are the
Yeah.
different ions that you are required to know by heart.
Okay.
So that then when you are looking at situations like this, you know exactly what the charge on them is.
Yeah. Yeah.
So these ones exist as ions already that your course AQA require you to know, and you also need to know the charges that each one has so that you can be in a position to break down an element, a compound such as this into its constituent ions.
Yeah. Okay.
Okay. Sometimes if say I had something like calcium oxide, on the other hand, and I wanted to break this down into its ions, well, what would this be? This would be Ca2 plus. And oxygen always receives 2 electrons, so it'll be O2 minus, like that.
Yeah. Yeah.
Okay.
Yeah.
So these are more or less special cases: the nitrate, the sulfate, and the hydroxide.
Yeah.
But we'll look at them again, like I said, in more detail in due course. So worry not. It's something that we will have to do shortly or very soon. Okay. Okay, great stuff. Next part anyway says student uses a pipette to add 25 centimeters of sodium hydroxide to a concentration to a conical flask. The student carried out a titration to find the volume of 0.1 more decimeter cube sulfuric acid needed to neutralize the sodium hydroxide. Describe how the student would complete the titration. You should name a suitable indicator and give the color change that would be seen. Okay, so there we go. That's 4 marks. Okay. Now, the key thing to note is, as well, something I didn't fully highlight, but I should have made a point of it. It's not here. Do I have it? No problem. Is that obviously to try and get a more accurate result, what you generally do is that you will repeat the experiment until the results are what you call concordant, meaning that there's not much of a difference in the values of volume that you're obtaining. So any result that is an anomaly, you do not include it, and then you average it. So it looks like this. So you do it once, second, third, fourth, fifth time.
And then find the average of it all.
And find the average, but you will ignore any anomalies.
Yeah,
It
yeah, of
tells you
course.
here, concordant results are within 0.1 centimeter cubed of each other. So anything that is outside of this range, you disregard it. Does that make sense?
Oh, okay. So anything that's out of, say it's greater than 0.1, you can't use it. You have to use the other ones that are in it.
Correct. So for example, there's this value 28.15. Compare this to 27.05.
Yeah, it's in that range, 0.1.
Yeah, 27.05, 27.15. You can see which ones are in the range and which ones to ignore. Okay. So let's so discussion then. I won't make you write this whole thing, but what do you think you might include in this? It says, describe how the student would complete the titration. So a student used the pipette to add, so if I just draw, there we go, that's your student's conical flask. and they've added, what is it again?
25 centimeters cubed.
25 centimeter cubed. And this is sodium hydroxide. We don't know the concentration, okay? And he used a titration, so he's gonna have a burette. Actually, that's not a good representation. So that's my burette, and it's got a little tap here, so I can control how much acid I'm adding.
Yeah.
In here would be my acid. Okay.
Yeah.
So how would the student carry out this titration? You should name a suitable indicator and give a color change. So can you remember anything we spoke about indicators? What indicators could you use in here?
Of course, the universal indicator.
Universal indicator is not advised. They do not want you to use universal indicator because the colors, it's very hard to tell when you hit that neutral point.
Yeah. Is there one beginning with P?
Yeah, the failing, yeah. Quite
And
a
there's
long
one
one.
beginning with L as well, and Litman.
Methyl orange, yeah, a litmus,
Litmus,
right?
yeah.
Litmus, you can use methyl orange, but of course we're gonna want to stick to one. So methyl orange, okay? So key thing is the phenolphthalein, what did we say? It's colorless in acid, but pink in alkali. So when you place it in here, let's imagine that we're gonna use this one, then we're gonna expect it to be pink, isn't it?
Yeah.
And once we've added the acid and all the reaction has finished, what are we going to be expecting it to change to for us to know that the reaction has reached the end point? So one of the key words we want to speak about there is end point.
Yep, so we'd want it to be...
How do you know that we've reached the end point? What color will this change?
Will it be pink?
Well, it's going to be pink in alkali. So before the reaction starts and you put drops in there, it's going to be pink.
Sorry. So would it be turn colorless because the
acid...
Well
done. The acid would just become more than it once all the sodium hydroxide is used up. You're absolutely right. So it's pink in alkali and colorless in acid. So I'm waiting, I'll keep adding this acid until this goes from pink to colorless.
Yeah.
And at that point, I'm going to look at what volume of acid have I added. Okay?
Yeah.
And then you repeat the experiment. So essentially, it's that procedure that you would write.
Yeah.
We've mentioned the indicator.
Doesn't it mean that there's more acid than alkali, so it's not neutral?
You're right. But that's the only way you can know that you've just gone past the neutralization point. There's otherwise no other way to know it if you think about it.
Yeah.
You need it to change color. Otherwise, how do you know if you've still got more sodium hydroxide? Or how do you know that your sodium hydroxide is just at the cusp of being used up?
Yeah, okay.
Does that make sense?
Yeah.
Okay, good stuff. So you talk about your indicator, what color it would change. Then you talk about your titration technique, using your burette, and then also ensuring that the reason why you're using that and that color change is indicating to you an end point. And then you'd also repeat the experiment again. Okay. There are other few things that are very helpful as well in terms of procedure wise. You might want to rinse this conical flask with the sodium hydroxide, just in case there was anything in there. And also this burette, you want to make sure you rinse it with the acid that you're going to use before you start using it. Because there may be another acid that was in there, and then it's going to affect your results. Okay. So those are a few things to note there. Okay. So D.
Okay.
Yeah, have a go at D.
So the student can... Okay, so we need to work out what's in the range of 0.1 of each other, centimeters cubed.
Good.
So Um, over there in range, and then 27.05, that's in range.
Good.
And then the 28.15 isn't, and the 27.40 isn't, so it's just these three.
Just those three. Good, man. Good stuff.
And then it says to work out the mean volume of 0.1 moles.
Yeah, to work out the mean volume of 0.1 mole of sulfuric acid used.
Okay. So you just add all these.
Good.
1 plus 0.5, and that gives you 27.15 times by 2 plus 27.05
Yeah, good.
gives you 81.35. And then divide 81.35 divided by 3.
Good.
And then you get 27.116, and it doesn't.
Okay.
Should I do 27.12 to 2 decimal
Well done.
places?
27.12. That is exactly what you're going to be using. Centimeter cube. Job done. Good. Next one now. Look at that. Four nice big marks there. See if you can get them, Jay.
Okay, so is it question E you want me to do?
E, yes, correct.
Yeah. So the equation for the reaction is calculate the concentration of sodium hydroxide. Okay. Two. And then H2. And and 3 hydrogens. 1, 2, 4 hydrogens, and then it's all balanced.
Balance good. No tricks there. Fantastic. Great.
Calculate the concentration of sodium hydroxide. So the sodium hydroxide is this.
Yeah.
And then, so what to work out the concentration is the equation is concentration equals to moles divided by volume.
Yeah. Good.
To work it out, you need to do you need to find the mole and you need to find the volume out.
You know the
No,
volume of sodium hydroxide that's been used?
Volumes, yeah, 25
Good.
centimeters.
So we're going to write that down. 25 centimeter cubed.
Okay.
Good. Do we know the volume of sulfuric acid that was used?
Sulfuric acid. Volume of sulfuric acid, was it 0.1?
No point. You've just calculated it in part D. It says, calculate the volume. So
is it 27.12?
27.12. That's the volume of sulfuric acid. Do you know what the concentration of the sulfuric acid was?
0.1 moles per decimeters cubed.
Well done, good. I think you've got sufficient information there
Yeah.
to start working towards an answer.
Okay, and then the volume, sorry, that's the volume.
Concentration?
That's the concentration. The volume is, was it, I can't remember what was it.
You've just
27
calculated it in part D.
centimeters cubed. Yeah,
Well
that's
done.
the, and now, so we do this volume times the concentration.
Okay.
So this is the,
Take your time.
yeah. Oh yeah, I remember what to do now. So 0.02712
Good, well done.
times by 0.1
Good.
gives you 0.2712 gives you 2.712 times 10 to the minus 3.
Looking good.
So that is your moles.
Good.
Okay, and then we now, so you know the moles, and it's a ratio of 2 to 1.
Yeah.
So you times this by 2.
Good man.
And you get 5.424 times 10 minus 3.
Good.
And now this is the moles for that. So now you do 5.424
Good.
10 to the minus 3 divided by 0.025.
Top man.
And you get 0.043 significant figure.
Yeah.
2169. And then you get an answer of 0.217 moles per decimeters cubed.
Okay. 0.217. What number was that? That's number 1. Number 1. Imagine you're more or less on the money there. Moles. Da 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 da. Concentration. There we go, Jay. So you got 0.217 moles per decimeter cubed, okay, for 4 marks, okay? And you got your value of 27.12. Again, good stuff. No problems there. Okay. I think the last part, what's the last part asking? Ah, F.
Okay. The student did another experiment using 20 centimeters cubed of sodium hydroxide with a concentration of 0.18 moles per decimeters cubed. Relative formula mass is NaOH equals 40. Calculate the mass of sodium hydroxide in 20 centimeters of this solution. Okay, we're on to another piece of paper.
Okay.
So equals the volume and then the concentration.
Okay.
And then calculate the mass of sodium hydroxide in 20 centimeters cubed of this solution. Okay, and then we know the equation, the concentration equals to mole divided by the, is it the mass? I think.
Relative formula mass.
Also relative
Sorry,
formula.
divided by volume. Sorry, I beg your pardon. I was thinking of you calculating the formula for moles. You're right. Divided by volume. Yeah.
Okay. So what you do is, you know the concentration and it wants you to work out the mass. So if we work out the moles first, then we can convert it to mass.
Sounds good to me.
So 0.02
Good stuff.
times 0.18
Good.
and that gives you 3.6 times 10 to the minus 3 moles.
Good.
And then you know this, and then use the equation mole equals to mass divided by relative formula mass.
Well done.
And then the relative formula mass is 40.
Good.
So 3.6 times. Oh, wait, hang on, I've got to rearrange it. So you're doing the moles times the relative formula mass
Well done.
times 40
Good.
equals to 0.144
0.144.
grams.
Okay, now that to me looks good. Since check 0.144. There we go, 0.144 grams, and you're absolutely spot on. Well done, Jay. This is a very, very tricky element of chemistry, and a lot of good students struggle with it, and you've done extremely well. Because I have to tell you that sometimes it does take 2-3 lessons in a normal UCSE class to try and get through titrations and things like that, especially the calculations. But you've you've taken it very well, Jay. So congratulations. Like to see what I've seen. And that is it pretty much really on stoichiometry. And the next phase of this now is just going to be consolidating what we've learned and moving on to further topics. Okay, I'm going to email you all the extra practice material as well. And also the mark schemes. This one already has a mark scheme, so you could go through some of the questions. And next session we have, if you've got anything that you want us to address from the papers, just let me know. All right.
Okay, all right, brilliant.
All right, and have a good day, Jay, and I'll see you tomorrow.
Thanks for the session. Cheers.
Yeah, no problem. You're welcome. Cheers. Ciao.